Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. We are currently discussing time series econometrics. We are in the topic of stationarity. In our previous classes, we have seen what is the importance of stationarity, what is a stationary process, and then we had a look at what is the importance of stationarity, particularly in time series data. And majorly, we have taken two type of models. One was the random walk model, and we demonstrated that these random walk models, they are non-stationary in nature. Then we moved on to the realm of autoregressive models, and therein we proved that these autoregressive models, if a condition of stationarity, that is the parameter of yt minus 1, that is theta 1 or whatever you take it as the parameter, if that is less than 1, so in an equation yt is equal to theta 1 yt minus 1 plus epsilon t, if this value of yt minus 1 is, if this value of theta 1, which is a coefficient of yt minus 1, is less than 1, then these AR models will have the properties of stationarity in them. So we have seen, we have all these, and we have seen the stationarity process. It is mean reverting, the effect of shocks dies out, the mean is constant or zero, although zero is not very common. The variance is constant, and the autocovariance, it is also a constant term. So these these things doesn't vary with time more prominently. So just take a look at if you take a look at the graphs, although these are all hypothetical graphs, but this can be attributed to a process yt is equal to mu plus theta 1 yt minus 1 plus beta t plus et, where if b is equal to 0, that is there is no time trend, mu is equal to 0 means there is no drift parameter, and theta 1 is equal to 1. So this is an example of a random walk model. So the very first equation can be written as yt is equal to yt minus 1 plus et, or we can say that yt minus 1, that is delta yt is equal to et. This is the random walk model. This is a different stationary process, and we can see, means we can remove we can get us out of this random walk model, we can get the stationary process by using the method of differentiation. Now there is the diagram would look like this. There is a sustained, it is not exactly there, it has a trend or something like that. There is a sustained movement in one direction, then again a sustained movement in the other direction. Next, the same model, beta is equal to 0, mu is not equal to 0. It means there is now the process is not having, the process is not over here, but there is a drift parameter. So mu is not equal to 0 and theta 1 is equal to 1. So that means it's a random walk model with a drift. A pictorial representation of a hypothetical case can be shown like this. Again, this is also a different stationary process, means if upon differentiating the series, you will get a stationary process. In this case, if the theta is less than 1, meaning thereby this is not a random walk model, rather an autoregressive model, and if the value of beta is equal to 0 and mu equal to 0, so it is the basic model with no drift and no trend. So we can write it as yt is equal to theta 1 yt minus 1 plus et. Again, this is a stationary process. We have seen before also, and the mean is 0, so the series is rotating, the variance is constant and it is around the mean. The next case, again theta 1 is less than 1, so this is a stationary process, and here mu is not equal to 0 means there is a term mu. So, if there is a term means there is a drift parameter. So, the series is not removing or fluctuating around 0 mean, but rather a different point which is above the 0, that is there is a drift parameter. Now, again here there is no trend. This is again we have seen a stationary process. Now, we see the third case. Here theta 1 is equal to 0, meaning thereby there is no value of yt minus 1. So, it is just a process where mu plus beta t, only the drift parameter is there and the trend is there. So, there is a trend, and since and it is rotating, this the variance is moving along the trend, it's fluctuating around the trend. So, as the variance is constant, although there is a trend, we can make this process, this is as such, this is not a stationary, but if we call it trend stationary, meaning thereby there is a trend, and if we remove if we remove the trend, then the process will become stationary. So, we can make this process stationary. I think now herein there is only the trend component over there. This is a random walk because your theta 1 itself is theta 1 is 0. So, if this is a drift with a deterministic trend. So, these are all examples of again this is an example. This is, if you see a diagram like this, the first thing which we should strike in your mind is this process is deterministic trend with an stochastic AR component, means the series is fluctuating very much over there. So, these are some of the process, but what the emphasis of this is, these diagrams and hypothetical cases, they, with them you cannot exactly identify what is the case. So, you need a definite process, a process with exactly a formula and all those things in order to identify what type of process is this. Now, we have seen what is a stationary process and what is a integrated process, that is a non-stationary process where the effect of the shock is integrated into system, the shock doesn't die out. Now, the random walk model is but a specific case of a more general class of stochastic process known as the integrated process. The random walk model with the drift was not stationary, if you recall our discussions, but it is at first difference it can become stationary. Therefore, we call this random walk model without drift as as I1. I1 means integrated at first order, meaning thereby if we do the first order differentiation, it will go away. Now, what is the process of differentiation? If you want to have a look, say we have a series 2, 3, 5, 9, 15, and suppose this series is not stationary. So, what we can do, this is xt, we take xt minus 1, this 2 we write it over here, this 3 over here, this 5 over here, this 9 over here, we do xt minus 1, it is x3 minus 2, 1, this is 2, and minus 5 is 4, and it is here 6. Now, this process is, this was not stationary, and if it is after first differentiation, if it becomes stationary, now this process is stationary. Sometimes we may need, in place of xt minus 1, we need xt minus 2, means this 2 we will write it further below, this 3 here, this 5 is here, and then we do again then we do the deduction process. So, if we have to do the differentiation once to get a stationary, we call it integrated of order 1. If we have to do integration 2 times, or we have to take 2 lags while differentiating, we call it integrated of order 2, I2. And if the process is stationary at level, we call it integrated of 0 order, that is Y0. So the thing is, we will be using this stationary time series and time series of integrated of order 0 and order 1. So we will be using this term in our I1 and I2. We will refer to as I0, I1, I2 in order to just give a feel that whether it is a stationary process or it is a non-stationary process which becomes stationary after first order differentiation or at the second order differentiation and likewise. So we will be referring to terms I0, I1, I2 and likewise. Before moving further, we have a look at what are the properties of this properties of an integrated series. If say there are two series X and Y, and if this series X is integrated of the first order and series Y is, no, if series X is integrated of 0 order, that is stationary series, and series Y is integrated of the first order, then series which is a combination of these two, that is another series we are making, ZT is equal to XT plus YT, it will be I1. Although one of the components of this series was I0, the other component is I1, but still the resultant additive of this two, it will become I1. That is a linear combination or sum of stationary or non-stationary series is non-stationary. We take the second case. Here see it is written X tends to Y tends to D. D gives the idea of how many different times differentiation is done. If it is done 1, then the value of D is 1. If it is done 2, the value of D is 2. If the differentiation is done 3, then the value of D is 3. So if we have a combination like this, that Z is equal to A plus B xt, this will be also ID where the alpha A and B are the constant. That is a linear combination of an ID series. Any linear combination, if it is I4, it will also be I4. If it is I1, it will also be I1. So if X is I0, then Z2 will be also I0. Now the third one is, so that is why we can use this OLS when we are having an stationary process. The third case is if X is ID1, D1 and Y is ID2, then ZT, if it is written like that, is AXT plus BYT, it will be ID2, means it will take the order of the higher one. There is one is D1 and the other is D2. D2 is greater than D1. So the resultant series of this type of combination, as shown in over there AXT plus BYT, it will be ID2, and we are means where we have the concept that D2 is greater than D1. Next is if XT is ID and YT is also ID, then Z is AXT plus AYT, and most of the time we denote it by ID asterisk. It is equal to 0, but in some cases D asterisk is less than D. This thing will be used in our discussions on co-integration. So at the moment we have just introduced you what are the properties of integrated series, and we restrict our discussion on these properties over here. When we move on to co-integration, we will be seeing the implication, we will be seeing the implication of this. Now, this is autocorrelation. Autocorrelation is the formula or the value of which helps you to identify whether the series is stationary or not. The formula for this is covariance upon variance, and this is denoted by rho k. The value of rho k, it will be always between -1 and +1. So what we do, normally particularly if you see any discussions on stationarity, or even you go to the realm of ARIMA, autoregressive integrated moving average, you will find correlograms are very prominently used over there. And this correlogram, this is not correlation, this is correlogram. So this correlogram where we plot this rho k against the lag, we will see to it. Now, for a non-stationary process, these values of autocorrelation function which we have just seen, this will be very high for many lags. This will be very high for many lags. If you recall a picture, this will be something like this, and this thing will be like this. It is declining, but still it is very high. So we can say that this will be this will indicate that the process is not stationary. And if it is this process, it's not. These are rough hypothetical, and a stationary process will be like this: one lag, second lag, it's finished. This will be a stationary process. So, if the value of autocorrelation function, it declines very rapidly, we can say that the process is stationary. Again, we have this white noise. If it is a white noise, that the value of autocorrelation function is 0 for any lag greater than 0. Now understand one thing, to plot this autocorrelation function, we need to have the entire time series, but many a time we are working with a sample of observations. So we calculate sample autocorrelation function. Now we need to test if the value of this autocorrelation function, the estimated value of the sample autocorrelation function is 0 or not. So for a series to be random, all rho k's for lag more than 1 should be 0. For a series to be random, all rho k values for lag, this is lag, for lag more than 1 should be 0. Now, we go for how this testing is basically done. So we have we can have two processes. One is where you check all the lags together, and this one is a process where we check individual lags. So Bartlett said that Bartlett's idea was that if a time series is purely random, that is, it exhibits white noise, then the sample autocorrelation function for any k greater than 0 are approximately distributed according to the normal distribution with mean 0 and a variance 1 upon t. So this we say is a normal distribution with mean 0 and variance 1 upon t. So if that rho k is equal to 0, the process is stationary. If that rho k is not equal to 0, the process is not stationary. So using the concept of normal distribution and the t-table values, they defined a confidence interval. Confidence interval for any rho k. So what it is? Rho k hat plus minus 1.96 multiplied by 1 divided by under root t for 95% confidence interval. Normally we take 95% confidence interval. If the hypothesized value is inside this confidence interval, we reject H naught, and the moment we reject H naught, what this means? We do not reject H naught, means we accept H naught, and this means H naught says our series is stationary. So if the 0 is inside this confidence interval, we accept H naught, means the process is stationary. We take an hypothetical example, t is equal to 196. So here t is the sample size in the sample. We do not use the terminology n, rather, because we are taking time series data, we simply say t. So t is equal to 196. So under root of 196 is equal to 14. What we basically are planning to do is rho hat k plus minus 1.96 1 upon under root t. So under root t is equal to 14, 1 upon under root t is equal to 0.0714. Suppose for lag 8, just we take an example of lag 8 is the value of rho k is equal to 0.65. The value of ACF, that is the autocorrelation function, is equal to 0.65. No, so for 95 confidence interval, this becomes 0.65 plus minus 1.96, and the value of 1 upon under root t is equal to 0.0714. When this is the case, so one time you have we do plus, one time you do minus, so we get the lower limit as 0.51 and the upper limit as 0.79. Now it is extending from 0.51 to 0.79. 0 is not falling in that within that confidence interval. So as 0 is not included in this interval, we reject H naught, that rho hat is equal to 0, which means that rho hat, this process is statistically different from 0. So when we reject rho hat is equal to 0, if rho hat is equal to 0, what is the case? If rho hat is equal to 0, the process is stationary. Since the rho hat is not equal to 0, we can say the process is not stationary. So this is one of the methods to measure methods to measure whether a process is stationary or not. So it means rho hat at 8. So means rho k at 8, that is the autocorrelation function at lag 8 is statistically different from 0. Now there is an alternate process. Now there is another alternate process which treats the same thing in a bit different way. Again we have all those same thing, that is here also we construct a confidence interval. It is 1.96 multiplied upon 1 upon root t, and we will do plus minus over here also. Now if the value of rho hat is inside this region, then we accept H naught. If the value of rho hat is outside this region, we reject H naught. Now what is rho hat of what is the null hypothesis? The null hypothesis is rho k is equal to 0. So if your rho k bar, it is basically rho k bar, here it is also missing. So if rho k bar is less than t alpha upon 2, that is alpha, if it's a two-tailed test, so we divide the alpha into two parts, 1 upon root t. So if rho k is equal to 0, the process is stationary. If rho k is not equal to 0, that is if the null hypothesis is rejected and the alternate is accepted, then the process is not stationary. We explain it with the help of an example. Say t is equal to 64, and so 1 upon under root t is equal to 1 upon 8, so this is equal to 0.125. Alpha is 5%, so it is 1.96. so what we have 1.96 multiplied by 1.25, so this is equal to 0.25. Now say for we take any lag 5, your rho k is equal to 0.68. So as this value of rho k is more than 0.245, so this is 0.68, the value of rho k at lag 5, as it is more than 0.245, we can say it will lead to the rejection of the null hypothesis. So if the null hypothesis is rejected, it means the process is stationary. If the null hypothesis is accepted, it means the process is stationary. So with this we have today introduced you to the concept of autocorrelation function, and we have just today seen if what would be the case if we want to check for individual lags. So now if you see that in this case, now these spikes are the autocorrelation functions. So if these spikes are greater than, these are the confidence interval. If these spikes are greater than the confidence interval, then the process is non-stationary. This is an example of non-stationary process, and if the spikes lie within this interval, this is a stationary process. So this is what basically your diagram for coloregram, which you will find normally in any book on time series, or even when you do the discussion on autoregressive integrated moving average models. So, now we have our, we take a few more notes nowadays. Uh, Till now, what we have seen, we are checking for the stationarity one single process. But if we want to check the stationarity of all the lags in one go, then we use Box and Pierce Q statistics. The formula for this Q statistics is equal to n summation rho k square, where n is the sample size and m, that is the summation k, it's from 1 to m is the lag length. Now this is approximated by a chi-square distribution. If q is can be approximated by chi-square distribution, q follows a chi-square distribution. If q square is greater than q critical, we again reject the null hypothesis. And similarly, there is one more statistics that is commonly used. This is the Jung box statistics. It is defined, it is also said as LB statistics. This is n plus 2 summation from k extending to m, rho k hat divided by n minus k. This is also, we check its significance by the help of chi-square distribution. But this one has a better small scale properties than the Q statistics. And both of these Q, Jung box statistics and the Q statistics, Box and Pierce statistics purpose is to test the joint hypothesis that all autocorrelation functions up to a certain lag are equal to 0. Hope our today's discussion on autocorrelation function is clear to you. We will continue with this in our upcoming classes. Thank you.